Welcome to Alexey. Thank you for taking the time. And this is a repeat performance today, but this is awesome to have Alexey here. Very timely and interesting topic. Neural texture compression. So over to you, Alexey, if you want to grab the screen.
Yes, I will be talking about neural texture compression, and I will briefly describe what neural texture compression is, how it works, and why it's good, and then move on to how neural texture compression can be integrated with the glTF format for using NTC textures or materials in glTF. Like how it was done in the prototype that is currently shipped and how it should be done. Like I will present a proposal to add an extension to glTF that allows using NTC and similar types of textures in glTF. Also, I should note that earlier this morning, I was giving the same presentation to another group and Zoom was crashing a few times. I tried to fix that, but if that happens again, I apologize in advance. Let's begin here. Neural texture compression, it's based on a research paper published in 2023 by a few NVIDIA researchers. Since then, there has been a couple, or at least a couple of follow-up papers, like one from Ubisoft, one from AMD, that are working to improve some aspects of this approach. But what we have productized is based on exclusively on our paper with some own improvements, like minor improvements made since then. So we have developed an SDK called RTX NTC, and that SDK is public on GitHub as of February. And the SDK has 4 key components. The first one is shown on the top here, the NTC neural texture compression library called libNTC, and it has 2 main subsystems. The CUDA subsystem that does compression and decompression of NTC textures or materials, and the Vulkan and DX12 subsystem that is designed for integration and use in like game runtimes and game engines or other rendering engines that do not use CUDA and they just need to take the NTC materials and use them for rendering. And that includes different decompression or inferencing modes, the inference on load and BC transcoding, and also inference on sample. I will talk about each of these modes in more detail in a few minutes. The SDK also ships with 3 applications. First one is the NTC CLI command line tool that can do compression and decompression of the texture sets from command line and inspection to, and it's designed to be used in like automation scripts and like level baking tools. Then the NTC Explorer application that just lets you load a few textures for a material and look at them individually or as a simple 3D plane with PBR properties and compress that material with NTC using different parameters and compare the results of compression to the original and to each other. And then the third application is the rendering sample. It's a very simple renderer that just loads a glTF model or several models. And those models are supposed to have NTC textures pre-compressed. There is a script that processes glTF assets and compresses their textures into NTC, and the renderer just picks that up. This SDK is currently available on GitHub if you follow the link here on the bottom of the slide. A few key facts about neural texture compression, about how it works. At first, it's that it's designed to operate on up to 16 texture channels at once. This number is, I wouldn't say arbitrary, it's caused by some GPU architecture considerations, but it can be changed, like it could be higher or lower. But our implementation produces 16 texture channels. Like if you need a location in the material texture set, you get all of those properties at once by doing the network evaluation, like base color, normal, roughness, everything at once for one location. And NTC works best if these channels in the textures are correlated, like if there's some detail in the base color texture that responds to a detail in the roughness or normal textures. Not necessarily like linear correlation, but detail should be in the same locations. Like if there is detail in one texture and the other one is flat, then some features from one texture can kind of leak into another, and that is mitigated by using a higher data rate, like lower compression ratio. And speaking of compression ratios, NTC has an adjustable output kind of bit rate. It's adjustable from half to 20 bits per pixel, and the number of channels also varies from 1 to 16. So overall, NTC can be used to encode from 1/32 to 20 bits per pixel per channel. The extreme values are not very useful, but something in the middle is. And typically we see a good quality with like 2, 3, 4 bits per pixel for regular PBR, like number of channels, like 9. And if you compare it with regular formats like BC7 or BC5 for some properties, then you can get up to 8 times smaller texture footprint in video memory compared to BC7 for the same materials. I'm not talking about PSNR here. With PSNR, if you target PSNR, you get slightly lower difference, but perceptually, it's still similarly good. Then NTC works by training a very small neural network for each material that it compresses. Basically, the network is just a small multi-layer perceptron that has 4 layers, up to 64 neurons in each one. And the compression of a texture set into NTC basically is the training of that MLP. There is no large model that does something. There is no large data set that was used to train a model, and there is nothing to produce hallucinations. Like that small MLP and the set of latents that it comes with is overfitted to decode one specific material. And if you are like, there is no variation run to run when you decode the same data. It's always the same. Like if you compress the same material multiple times with different initial random seeds, you will get slightly different noise patterns, but that noise pattern is not very far from the original, and the decoded versions are always the same. The compressed data that comes out of NTC contains the latent representation, which is basically a tensor of numbers whose size is proportional to the size of the original textures. And that latent tensor or feature grid or feature pyramid, it takes almost all of the space of the compressed texture set. And then there are the weights for the MLP that take something like 12 kilobytes, regardless of the resolution. Briefly, how NTC works. For decompression, it's going left to right on this diagram. Let's say we are trying to decode a set of PBR channels for a given texture position. We get the UV coordinates of the texture position and map those to the feature tensors, the low res and high res one. We sample, like we do bilinear sampling basically of these feature tensors, and we get features. Those features are put into a vector along with the positional encoding here in the middle, and that vector is used as the input to the MLP. The MLP is evaluated, and the output of the MLP plus some scale and bias is basically the original colors of the textures. So you evaluate a network, you get colors for one texel. The network is small and it doesn't do like a bilinear interpolation. Instead of that, we can use stochastic texture filtering. I will talk about it a little later. So I mentioned that there are multiple inference modes supported by NTC. It's important to understand the differences here. First one, like what was originally described in the NTC paper, is called inference on sample on the left here. And the idea here is that we take the NTC compressed data, all that latent tensor and the weights, and we keep them in video memory. When we are rendering some model, some triangle with an NTC material, for a given pixel, we know the position that we need to sample. We apply stochastic texture filtering to translate a fractional UV and the filtering mode into an integer texel position, and decode the NTC texture set for that texel position. We get all the channels at once, and we use that for those for shading. STF, stochastic texture filtering, works in a way that on average, like you use these integer texel positions, but on average, if you render for many frames, they use something like DLSS to smooth that. It will integrate to the right solution as if you were using a regular bilinear, trilinear, or anisotropic filtering. The benefits of inference on sample are that it produces the minimal possible VRAM footprint. Like I quoted something like 8 times smaller than PC, or maybe 4 times if you increase the quality. But the drawback is also quite significant, is that the decoding of NTC textures is quite expensive. Like if you use it in a simple gbuffer pass, for example, or in a ray tracing pass that does the primary rays, it's fine. But if it's used in a more complicated shader, like in a path tracer, it can significantly affect the performance. And it also works best if the GPU has tensor cores and supports the new cooperative vector APIs. If it doesn't, there is a fallback solution, but it's kind of slow. And for those fallback GPUs, for legacy GPUs, we have a mode called inference on load, where we basically take the NTC texture set and decompress it when we load it. The compression happens entirely on the GPU. It produces the original colors, and those colors can be fed into a BC compressor that we also ship with the NTC library. Our BC compressors are very performant. And overall, if you have a material with like 2 BC7 textures and 1 BC5, you can transcode that at the performance of like a few gigapixels per second on a high-end GPU, which means it's practical enough to do on lower-end GPUs at load time. Like it doesn't take too long to decompress NTC and transcode it to BC. And if it is too slow, you could do it in a tiled fashion, like spread the transcoding of a single texture over multiple frames. The benefits here is that it's much faster than doing it on sample, because the GPU basically works with the BC7 or BC whatever textures as it usually does. There is no extra cost at runtime. There is no requirement to use STF, and it works everywhere-ish. I mean, the NTC decoding still needs a shader model 6 type GPU, but nothing very special there. It works faster with cooperative vectors, but they're not required. But the obvious drawback is that you don't get the VRAM savings that you could get with inference on sample. The third mode is called inference on feedback. We just recently published that, shipped it with the NTC SDK update. And it's basically an NTC-enabled virtual texturing system where you have sparse textures that are allocated for the models that you currently have loaded, but they're originally empty. And the texels, like the contents of these textures, are only streamed in when necessary, and the necessary set of texture tiles is determined using sampler feedback. There are other ways to determine the set of tiles, but sampler feedback is kind of the hardware-based new solution. So when we determine that some tile or set of tiles are necessary to render the current view, we can schedule them for decompression or for transcoding, and that will be done on the next frame so that the textures are streamed in. Because NTC library supports decompression, transcoding in a tiled mode. And the tiles are transcoded into BC and stored in the tile resource. So the benefit here is that we get a pretty small impact to the renderer shaders. You just need to do the sampler feedback there. And you get fast sampling because the GPU, again, uses BC textures or raw colors if you don't support BC. And it's also significantly lower VRAM usage compared to fully mapped textures, just because typically you don't need all of the textures at the highest resolution, and you can get something like 5 times memory savings. But obviously this requires an implementation of virtual texturing system in the engine. So few words about NTC quality. Basically, why it matters is that it gives you a significant compression ratio over BC at the same size, at the same quality level, or conversely, at the same size, you get significantly higher quality. There are some factors that affect the image quality. Obviously, texture contents being the primary one. Like if you have a lot of small and high contrast detail in the texture, it's more difficult to encode, so it takes more bits to encode that with high accuracy. And of course, the compression ratio, or the bits per pixel of the compressed texture set, is very important too. Typically, there is a monotonic dependency of the output quality, or PSNR, from the bits per pixel value, which is shown on the plot on the right here. Like there are five curves here that represent compression, or that represent the quality of compression of 5 different materials versus the bits per pixel value that was used to encode with NTC. And those are compared with the various BC formats that could be used for the same textures, for the same materials. And as you can see, the BC points are kind of far on the lower right compared to the NTC ones, which means it's just we get higher compression than NTC. And like I mentioned, the latents that NTC produces, they take about 99% of the compressed data, and they generally don't compress much further with, they don't compress much further unless the texture has a lot of flat space like that sign in the number 5 example here, in which case you could use something like zip, LZ4 or something like that to compress the latents. So I can talk about the details of the NTC texture sets and the proposal of how it integrates into glTF, but previously Neil suggested that I insert a demo here, so I'm going to do that. And my demo is basically taking the original glTF model that is available from the Kronos sample assets repo, the flight helmet. Here are the files for that model. It's a glTF file, the buffers, and a lot of textures. I have a script here that can take the glTF file and convert all the materials in the glTF file into NTC textures. So it has analyzed all the materials and the textures that they are using, and it also detected that different materials in the same file are using the same texture. So it has merged the texture sets for these two materials into one NTC file to avoid duplicating the data here. And currently it's running the compression. It's doing that on 2 GPUs. It takes something like 10 or 20 seconds to process each material. So it will be done in a few seconds here. Just the entire scene compressed live as we're speaking. And when it's done, I will show how it affects the file size and how it renders. And it's done. So it produced these 5 material files that total take 4.7 megabytes, whereas the original PNG files are 43. So it's like a 10:1 compression ratio. For BC textures, it's different, but comparable. Yeah, comparable. And I can take this new glTF file and use it with the NTC renderer. It's taken the NTC files, decompressed them either on sample currently or on load. There is no visual difference. It's the same data, just difference in how it's used and difference in how much memory is used. Like for NTC on sample, we use almost 7 megabytes of memory to store all the textures for this model. For NTC on load, we transcoded that to BC7 and BC5, and we take about 100 megabytes, which is a significant difference with there is no visual quality difference because we take the NTC data as the source here. I can also show how it works with the reference materials or the original PNG files. It takes a little longer to load, but and this label here isn't correct. It's just the original uncompressed materials. It takes 270 megabytes of video memory this way. Now on to the details. So NTC texture sets, they contain multiple textures. Like I mentioned, they are designed to store the entire PBR stack for a single material. So here I have an example of 3 PBR textures for a single asset, like some tableware here, the base color, the ORM, and the normal map. The manifest file shown in the middle, it lists these textures and explains how the textures are supposed to be used, how the textures are supposed to be loaded and placed into the NTC channels. So we explicitly say here that the albedo or base color texture is to be placed into channels 0 to 2. The ORM texture is swizzled. We swap the metalness and roughness and place them into channels 4 and 5. and the occlusion is ignored. It's optional. And the normal map is placed in the channels 8 through 10. The manifest also specifies that the base color is supposed to be transcoded into BC7, as well as the normals, and the metal roughness is supposed to be transcoded into BC5. This is basically just metadata. The implementation or render is free to ignore that, and that's just a hint. It's stored in the NTC texture set, and it can be used by the renderer to do inference and load. Now, how that was implemented in the SDK that we are currently shipping, it's shown on this kind of code snippet, but the requirements or the idea with that prototype implementation was that we have one NTC texture set per material. We don't want to sample 2 of them for pixel. And multiple materials of a glTF file or multiple materials in a set of glTF file may share the same texture set. So there is a like there can be a many-to-one mapping of glTF materials to NTC files. The rigid assignment of PBR channels to NTC channel indices was done to avoid dynamic indexing of the MLP outputs in the shader, because you don't really want to do dynamic indexing in shaders that are just slow. And I also wanted to avoid any app-specific modifications in the framework's glTF loader. So there is no hacky glTF extension here. I just stored the mapping of the material indices to NTC files in a separate text file. This is horrible. Don't do that in practice. It's just something hacky that worked for them. So a better solution that I'm actually proposing here to integrate in glTF as a vendor extension is to add support for sort of multi-channel image slices. So normally with glTF, we have this material definition that has PBR slots, like the base color texture on the left that indexes texture number 0, that refers to an image file, also number 0, etc., etc. Like each texture has its own image file. I suggest to add an extension that allows us to describe that the texture doesn't just refer to a single image file, but a set of channels from an image file. Like here, we take image number 0 from the bottom. It's in the NDC file. And we take channels 0, 1, and 2 and combine them into a texture that is compatible with their standard glTF layout for base color. Similarly, here we take channels 6, 4, and 5. We like shuffle them. That's also an option. And we use that for the ORM map. Optionally, I'm suggesting here to add an attribute like array slice. The current NTC implementation doesn't have support for texture arrays, but that's something that can be added. Like if you have a UD atlas, for example, that has multiple slices, you could index into those from a single texture file using the array slice feature. But again, it's currently not implemented. And alternative, simpler solution here is shown on the bottom, where we, instead of channel shuffle or swizzle, we take just a slice from the channel set, like number 8 and 3 channels starting from there. But it's less verbose, but also less flexible. Like you couldn't do stuff like that here. This shown on the bottom here is a suggestion for a new MIME type for NVIDIA NTC format, but it's kind of entirely optional because the NTC format is not stable yet, I would say, but the multi-channel image suggestion is generic enough that it can work with other potential implementations of the NTC compression and even with non-NTC formats like EXR. Alternatively, I can suggest decoupling the image multi-channel image slices from texture definitions and placing them in a separate new construct in the glTF file called image views. And that can allow us to explicitly deduplicate the image slices from how they are used in the glTF file. Like if you can if you want to, for example, use the same image slice with different samplers. I'm not sure why you would, but it would be possible explicitly here, although it doesn't really bring any new information, and some deduplication can be done on the loader side with the previous version. So it's just an alternative. I'm not sure if it's worth seriously exploring. Now, there are some potential issues with the proposal. One is that NTC in general doesn't really work well with, like NTC inference on sample doesn't work well with some of the glTF features like texture transform that allows you to independently scale and rotate and move the textures applied to a material. And the reason is that when you do inference on sample, you get all the channels together from a single texture sample and a single location. So if you have different sampling positions, you would need to do NTC decoding multiple times, and that would be very expensive. For the same reason, it doesn't really work with different samplers for textures or different texture coordinate sets. And like I mentioned, we use a stable or well-defined mapping of PBR properties to channels in the NTC texture set for performance, but this can be left up to the implementations, and we can also do things like shuffle the MLP rows or columns in the last layer to alter the order in which the channels are output from the neural network to avoid dynamic indexing here. It's just something that is possible, but not currently implemented. The extension that I described, the multi-channel image, it ignores all of the NTC metadata, like the channel mappings, the texture names, transcoding formats. That metadata is still possible to be used by renderers as hints, but it's not necessary. Like using the extension, using the multi-channel image thing, you can take an NTC-enabled glTF asset and render it unambiguously. The rest is just hints. And it also makes it flexible enough, like I said, to support potentially other implementations of NTC and other formats that have multiple channels in one file. And like I said, I'm not suggesting to standardize the NTC file format yet, because there are still, we still don't know if it's going to change. We don't have any real world adoption of it yet. We don't know any real world issues with it, and there's still research ongoing. So changes are likely within the next, I don't know, year or so. A little bonus here is a description of the NTC file format itself, the way it currently is defined. The file is loosely modeled based on binary glTF or GLB. It has a container header that just stores the offsets of the two chunks in the file, offsets and sizes of the two chunks in the file, the JSON chunk that's shown in the middle, and the binary chunk that shows that's shown on the right and stores data like the MLP weights and latents. The JSON chunk describes like the geometry of the texture set, a number of features, how the MLP is structured, etc., and all the metadata. And it points at the data that is located in the binary chunk. The full specification of this format is available on GitHub following the link on the bottom. While we're at it, a little bit of extra requests. We sometimes saw that the GLB format is not sufficient to export large assets. Like if you have large textures or geometry, we can just overrun the capacity of the binary buffer, which is defined as a single uint32. So using uint64 here would be much more practical, although that would be a breaking change. And that's all I had to say.
Awesome. That was an awesome presentation. Thank you, Alexey. Virtual round of applause for Alexey, please. So, any questions? So, I mean, to kick things off, kind of similar to the discussion we had on the previous presentation earlier this morning. I mean, can you comment on the last slide there, or close to the last slide? You're saying it's not quite ready for standardization yet because there's still R&D. We need implementation and industry feedback. What's your view on what kind of time frame would be good, and what can we do as a community to help feedback into that process?
So for standardization, there are two aspects here, like I described. One is the glTF extension for channel slicing, the multi-channel image. I think that doesn't really depend on anything else, and that can be discussed and standardized or accepted as a vendor extension, I guess, for glTF now, or after some discussion, I guess. The NTC format itself, like I said, I don't know what changes that will happen to it over the next maybe year or something like that. I guess we will we'll know more after some integrations happen into game engines. Maybe somebody tries to actually use it. The format itself is it's designed to be kind of flexible, but it obviously we can find ways to break it or to do things that are not supported by the current format, and it has to be extended or changed in some ways. And also there was some discussion earlier this morning about how NTC coding is kind of PC centric. You could technically decode it on anything if the format is well stacked. So it could be used as a storage format or transmission format, but let's wait until we have some more data and stabilize on the format itself. And as long as like what people can do to help us, there is just, I guess, try to use our SDK that is available on GitHub, see if it works, if it doesn't, and provide comments.
Yep, that sounds good. Ed, you had a hand?
I do. So do you have thoughts about supporting additional PBR inputs like clear code and sheen and transmission? Typically in glTF, we often see sort of different mappings in different materials. So there might be a material that's just core PBR, and then there might be a material that has a clear coat texture applied to it, and then there might be a separate material with a transmission texture or something applied to it. And would those be separate NTC files? And is that supported, that different materials would have different mappings like that?
The specific set of PBR channels doesn't really matter. Like you can store whatever you want in NTC textures. They're not specific to any type of data. Like you can take any number of textures of any type, and as long as they pack into 16 channels, that's all good to go. And the proposed extension for the multi-channel slices, it's still compatible with all types of PBR channels. It doesn't really matter how it is used.
Okay, cool. Thank you.
Thanks. Nick?
I thought that was really cool. And I was really intrigued by your proposal for like multi-channel indexing and setting slices and stuff. I had to write heuristics for EXR in USD in order to deal with, the way layers are named and organized and things. And it really just sort of drops all the utility of these kinds of formats on the floor by the fact that we don't have facilities like that. And so I was wondering, as I think I will always wonder in these meetings moving forward, if we might also have simultaneous USD proposals to correspond to that idea. My thought is that I'd like to see the two formats kind of evolve hand in hand with the same features like emerging simultaneously. I thought this like solves a lot of really interesting problems that the USD side has as well.
Yeah, thanks. I'm not really familiar with the USD internals, so I cannot comment on how feasible it is to do it there, but I suppose somebody can take a look. It's a simple enough idea.
Yeah. So I'm sure there's people on this call, myself included, who could help you figure out how to get that rolling. But
Yeah,
I would really like to to see it emerge simultaneously.
Yeah, no, a big plus one for that, Nick. And I think, no, correct me if I'm wrong, Alexey, but no, everything Alexey is doing is publicly available. And of course, yes, we have lots of USD expertise. So it would be great. It would be awesome to do it, to do it in parallel.
Yep.
I did ask Alexey about that, but as Alexey says, he knows glTF more than USD personally. But yeah, that would be a great idea. Joachim, go ahead.
Thanks for the presentation. Are there any plans in the long term to support this texture compression directly in silicon so that there is not anymore this performance overhead?
I cannot really say anything about like plans for a few years ahead. Currently, there is no dedicated silicon for NTC decoding in the GPUs, and I mean, there is silicon in the Tensor cores or equivalent things in other vendor GPUs that can be used to accelerate NTC decoding. The only part that is slow at this point is the fetching the features and the preparation of the input feature vectors. And obviously also takes a lot of registers to do NTC decoding. And the format and the decoder architecture is not stable enough yet for us to really consider implementing it in silicon. Maybe in a few years we will have something that everybody is happy with and then consider doing that, but not yet.
And maybe it's worth re-emphasizing, Alexey, that the shader there's backup implementations, right? You don't even need tensor cores or anything. You can just run it in standard shaders.
Right. It runs on standard GPUs, just slower.
Mm-hmm. Right. Cool. Any other questions? I see Henrik has turned
his
speed.
For Ed or Mike or anyone else deeply involved in glTF. So how common is this that you might have different texture transforms for the different channels? Like, that would be one limitation, of course, that Alexey mentioned. Is that something that is commonly used in practice, or how would we potentially deal with that if we want to incorporate something like this more, like on a broader scale?
Ooh, that's a good question. Sometimes people, I think, use that for maybe detail maps, but I think that I have to think about how and why people use those transforms. Certainly, I've seen models use a completely different texture coordinate set. It's a little more rare, I think, to use the same set with transforms, but of course it doesn't matter. Both are equally bad for this kind of setup. And the other thing we've seen recently is we introduced the KHR animation pointer extension, so we can actually animate a glTF texture transform and actually slide the texture on the surface. So it's not a huge deal breaker for most models that if you went with this, you'd be constricted to just use a single texture coordinate index per material, essentially. And it'd be interesting even, I think, to have some way, which we don't currently have in glTF, is to specify sort of a global texture transform. If you wanted to animate the texture, but you wanted all the channels linked together as you animate it because you were using NTC, it might be nice to have like a global texture transform somewhere, because I don't think NTC would be bothered by having it change from one animation frame to the next, as long as the lookup through all the different inputs is all from the same place in the texture. That's sort of my understanding of it.
Yeah, no, that makes sense. I mean, yeah, so obviously you wouldn't necessarily be able to leverage this in every situation, but for most models, the vast majority, you could still use NTC and reap the benefits. So maybe same question for Nick in USD land, like how common is it that you would have like separate things for the different channels versus having them combined?
Amusingly enough, that's the 100% case. I'm not sure why it's not represented in USD today, honestly. We generate hundreds or thousands of AOVs, which means channels, for every scene or object that we render in a film. But we output them to individual EXR files due to a lack of representation of these concepts. Then we put it through a tool called a stapler that creates an EXR with all the channels and the mapping in a single big EXR. And then that travels through the pipelines and goes to various compositing tools and things. And then when it hits the point where those AOVs need to be accessible again as texture bindings, we have to unstaple them and blast them apart into zillions of files. So is that the answer to your question?
Thanks.
Yeah, cool. All right, we're almost at the top of the hour. Any last questions for Alexey? All right, then again, thank you, Alexey. Another round of applause. It was awesome. I think you've initiated a number of really interesting threads that will hopefully come to fruition over the next, well, the short term and longer term too. So thank you.